Welcome to a demonstration of the Fourbar program. I'm Professor Norton. I wrote this program and it's distributed with my textbook Design of Machinery. This is the first of several videos that will demonstrate how the program operates, and this one is intended to get you started, to show you the basics of the program, and in later videos I'll give you some tips on how to use some of the more advanced features of the program. When you first run the program, you are greeted with this splash screen. You can either abort the execution or start the program, which I will do. This brings up a disclaimer screen that tells you that this is intended for uses for educational purposes by students and teachers, etc. So you should read that to understand what the purpose is. This screen gives you a place to put in your name, and that name will appear on all of the, or most of the output screens that you later generate with the program. In this box you can type any name you want for your particular exercise, and that will also appear on the screens. This gives you a further information about the limits of this student version, and you have to agree to these terms to proceed. That finally gets you to what I call the home screen. This is the screen from which you will launch and end all of your program operations in this particular software. When you first encounter the screen, the only buttons active are the input and the quit buttons, but some of these drop-down menus are also active. One thing that you might be interested to know right off the bat is that there is online help available. Under this help drop-down you can actually access the user manual for the program. This comes up in a scrollable window. This also can be zoomed. This in fact is Appendix A of your textbook, reproduced here for your convenience. And this describes not just Fourbar but all of the programs that come with the book, at least those that I've written. You can close this window out, bring it back at any time. There also is additional help for various menu items that you can bring up from these drop-downs. I'm going to just plunge in with a demonstration of how the program works. I'm going to be your help menu today. So let's move first to the input screen. That switches to this image and presents you with the opportunity to type data into the program with which it will cause some calculations to happen. The paradigm for the program in terms of the interaction by you is that any box that is yellow in background can be typed in, and any box that is a magenta, this is a cyan color, in background is feeding back information to you and thus is not available for typing. In the upper left-hand corner there is a choice with these radio buttons of either open or crossed mode for the linkage or circuit of the linkage. This is explained in Chapter 4 of your textbook. I would leave it at the open for the moment because it's we don't know exactly what we need at this point, but you might on a given occasion prefer the crossed mode. I'll show you what those do in a moment. The modulo choice lets you export and show your calculated angles either on a scale of 0 to 360 degrees or plus or minus 180. Here's where you type in the lengths for your links. I'm going to bring a picture up on the screen so I can point to what these things represent. I just hit the calculate button at the lower left and I provide you with some built-in data when the program wakes up, which is this particular linkage. Link 2, or the crank, is the link that connects the fixed pivot at where the input is provided with link 3, which is the coupler. So the lengths of those two links are here, 1.115 for the crank and 2.5 for the coupler, and that dimension represents the distance pin to pin of link 3. Link 3 also has some dimension down here, which I'll speak to in a moment. Link 4 is the rocker, and that goes from pivot 04, as labeled in your book, up to the join between link 4 and link 3, which would be called instance center 3-4, if you've gotten to that terminology, which is comes up in Chapter 6. I'd call this O2, or possibly instance center 1-2. Link 3, as I said, has some dimension to it other than just a line, and that creates what's referred to as a coupler point right here. And that coupler point is defined, for the sake of the program, by two dimensions. In this case, they are polar notation, and that's your only choice. So that's defined as being a distance 1.697 at an angle of minus 92.66 degrees from the left-hand end of link 3. In this particular case, more correctly, the end of link 3 that joins link 2, or instance center 2-3, another way to put that. So here's 1.697 inches at an angle of negative 92.66 degrees. That defines this coupler point. If all of this seems a bit confusing, you can pull down this help menu, and that will take you to the page in your user manual that displays this linkage geometry and how it's arranged. You can zoom that up a bit with the zoom tool here. And this labels the things I was just describing. There's your link 2. There's delta 3 is that 92.66 degrees. In my example in the program, it's negative, so it's going to the clockwise from the line of centers of link 3. That's link 3. There's link 4. There's 04, 02, the pivots of the two fixed links. And there's point P, which in my example on the page we looked at a moment ago is down here someplace, but it can be anywhere in the plane you like. Omega 2 is the input angular velocity to link 2, and alpha 2 is the input angular acceleration, if any, and theta 2 is its input angle. There are several, actually 3 coordinate systems that are at work in this program. The global coordinate system, which I set up through the driving pivot of the linkage, in this case 02, and it runs normally by default through pivot 04 for the x-axis, and y is perpendicular to that. Caps indicate global coordinates. Anywhere I wish, I can place a local coordinate system. My notation LNCS refers to a local non-rotating coordinate system, and I've shown one here at point B, which is instance center 3-4 as well. I also show another one over here at point A, instance center 2-3. In addition to those, I can have a local rotating coordinate system, which is essentially painted on the link. Here I show one embedded in link 3. Those I label with primes, x prime, y prime. So that's physically part of link 3. So back to our program on our picture. Recalculating will bring the image back up. So I've described now how the moving links are defined. I haven't yet described the fixed link, link 1. That can be input either as Cartesian or polar coordinates. You switch between those with this pair of buttons right here, and notice that it changes the colors of the respective boxes. So I can only type in the ones that are yellow at the moment. So if in fact my axis lies along the link 1 or vice versa, then I can put it in this polar coordinates. The magnitude here is 2.667 and its angle is 0. Or I could kick that link up at, say, 30 degrees. I'll type 30 in there, recalculate, and now my linkage is up at 30 degrees with respect to the x-axis, and I've simply rotated the linkage on the paper. I haven't changed the shape of the coupler curve or anything else. Over here on the right side of the screen is where we control the calculation mode. Note down at the bottom it's telling me that this thing is a Grashof linkage, and if I change the dimensions to something that is non-Grashof, it will so inform me here at the lower right. Up on the upper right hand corner I have the choice of angle steps, time steps, or single position calculations. It defaults to angle steps when the program wakes, and in that mode I can give it a start angle. Here is 45 degrees, an ending angle, which is 405 in this particular case, a delta theta, 10 degrees, and an omega 2, an initial, or actually constant in this case, angular velocity of link 2. Now the reason the screen went blank was when I clicked in these things it thought I changed them, and when it thinks you've changed something it blanks the screen so that you're not looking at a picture that's different than the numbers you have selected over here. This AutoCalc button If I turn that on, then every time I change something in any one of these windows, it will recalculate. If I change that to 5 degrees and move off the box, it will recalculate. You probably want to leave that off because it can get frustrating if you're trying to make large changes in link lengths, because as it recalculates you may get into a non-Grashof condition. So I would suggest you leave that off. Alright, this lets me tell it where to start and where to end with respect to the angular motions. But I also could operate in respect to time. If I switch to time steps, these boxes will change and the labels will change, and now I give it a start time, an end time, a delta time, an initial condition for the angular velocity of link 2. Omega 0 is referred to as the first angular velocity of link 2. Alpha 2 we would normally not have as 0. Let's make it 3 radians per second squared. And theta 0 is where it would start. I was starting at 45 before, so let's leave it at that. And if I now calculate, we see a similar picture to before. Here's my coupler curve. But note now that the coupler curve's dots, each of which represents a particular position of the input crank, are no longer equispaced, because what I've told it to do is to accelerate link 2, alpha 2 at 3 radians per second squared. So now my increments are no longer uniform. If I go to one position, then again this menu changes over here, so now all I get to tell it is what is the speed at the position I'm interested in, what is the angular acceleration, and what is the particular angle. And if I make that calculation, I see it in one position only, no coupler curve because it's not moving. So take your choice as to whatever suits your purposes here. I'm going to go back to the angle steps. Now I can move this around to get a sense of the motion by grabbing this slider at the bottom and dragging it, and you'll see the linkage move through all of the positions you've calculated. I can also step it, and that's essentially just moving that slider bar in equal increments. It does the same thing. And if I hit this animate button, I'm going to move to a different screen, which looks very similar, but has some additional features, and actually has lost some features from the previous screen. My open cross circuit relationship is now up here. Let me show you what that does. If I switch this into crossed mode, the linkage changes appearance and the coupler curve changes drastically. It is actually a different linkage. There are two solutions to the position equation for a Fourbar linkage, and I refer to them as the open and cross solutions. It corresponds to the plus and the minus sign in the equation, and physically it corresponds to assembling the linkage in a different condition. And if you hold link 2 right here at its present location, which is 45 degrees, decouple link 3 from link 4 and rotate them both down to this fourth quadrant neighborhood, you'll have the crossed condition. So now link 4 is going south, link 3 is down here intersecting link 4 in the other of the two possible solutions, which are at the intersections of two arcs, and I have a different linkage. So you have to determine which of those you want, because the equation doesn't know which you want. Either is a legitimate solution. On the left here, I can still change my link lengths if I so desire, my location of coupler point. I can change my pivot coordinates here. Here they're being shown in Cartesian. I actually put them in as polar, typing in 30 degrees. And over here I have some control over my solver still, my initial conditions and my final condition and my delta. The omega 2 and theta 2 are now fixed. I have to return to the previous screen to modify those. But the main feature of this screen, if I can wake it back up again, is the main feature of this screen that is different than the other is that I have a run button over here. And if I hit run, it drives the linkage through with all of its possible motions. That went rather fast. This computer is relatively fast, so I can slow things down with this animation speed button over here. That's still fairly fast. I can change the range of this slider by increments by dropping this menu down. I just doubled it from 10 to 20 so that it has more effect. I might even need more than that. I'll go to 40. Try it again. Now it's going slow enough so I can watch the motion. So you'll have to adjust that to suit your particular computer. I can't tell in advance how fast the machine you're going to run this on. So this is open loop. You'll have to determine what you like there. Okay, I can change this number of cycles to be more than one, and that will just make it go around, in this case 3 times, if you want to get a better look at what's going on. Another thing I can do on this screen is turn on trace, and when I run it now, I'm not going to erase the intermediate positions, and you see all positions that you have calculated, and it gets a bit busy, but you can now see the patterns of the links if you so desire. I can suppress the links to see the coupler curve, or vice versa. Put the links back on, turn off the coupler curve, run it. I meant to turn that off. Let's turn that off and see what happens. There we go. Okay. The other thing I can do is turn on this coupler line option. Now what I'm going to do is show you for each of the calculated positions. Let's make this at 10 degrees and get fewer of them. It'll be easier to see what's going on. Recalc. So now every 10 degrees of crank position, that is every 10 degrees of link 2, the coupler is at one of these circles, and the line drawn through the circle represents the angle of the coupler. So I get a sense of what the rotation of the coupler is at each of those positions. That angle is drawn at some reference, in this case 90 degrees, to the line of centers of link 3. So notice those lines are virtually horizontal here, and this link is virtually vertical. If I change that over here to 0 and I recalculate, I just run, notice that the lines are now in the same direction as the edge of the link. So you can orient them any way you want to get a sense of how this thing is moving. I'll put it at 45. Okay? Let me turn those off. Now another nice feature of this screen is I can make changes to my linkage without typing link lengths into the boxes. If you look up at the top of the screen, it says shift click drag on these various items to change the coupler curve. It's defaulted to coupler point. So what I'm going to do is hold down the shift key. You can't see my finger doing that, but take my word for it. I have the shift key down. I'm now going to put my cursor near the coupler point, click, and drag. And now as I drag, you see the coupler curve change. And if I drag it over in this neighborhood over here, I pick up a crew node. I didn't mention it, but you probably noticed that where I started out, I had a pretty good cusp on that curve. There it is right there. So there's a sharp corner here called a cusp. If you've watched the videotape on coupler curves or read that section in Chapter 3, you'll know what I'm talking about. And I'm going to continue to move this coupler curve, coupler point I should say, which affects the coupler curve. If I bring it over on this side, I start to get a sort of a flat-sided curve. Maybe I can get a approximate straight line motion out of that. If I move it a little bit further, it starts to look a bit like a banana, etc. So if you've looked at all at the Hrones and Nelson Atlas video or have read that section of the book, I've more or less got a dynamic Hrones and Nelson Atlas in here because I can see the effects of moving the coupler point around. I can also see the effects of changing, for example, the rocker length. So if I select a rocker up here, I've got to grab the end of the rocker. Now I'm holding the shift key down to activate this, and I grab this and I'm making drastic changes now. I just went non-Grashof. When that coupler curve gets interrupted like that, notice over here the label has turned to non-Grashof. So the linkage no longer has any links that can make a full revolution. There's also a videotape on the Grashof condition, which you can view. Read about that in Chapter 2. I can't reach all the positions, so the coupler curve is interrupted. If I drive it from link 2, it's going to lock up and toggle at those positions. So if what was I changing? The rocker. So if I lengthen the rocker, I should go back toward the Grashof there. I'm in Grashof land now. And I could change any of the others of these. If I change the coupler length, you'll see similar effects on the linkage there have gone non-Grashof again. And it's very sensitive to that. I don't have to move that very far before I get a drastic change in the curve. There's a curve with 3 loops. Yeah, the coupler curve is a 6th degree, thus called a sextic, and it's tricircular, indicating it can possess 3 loops, which you're witnessing right here. There are 2 crew nodes, and it's approaching a cusp here. If I move that a little bit further to one direction, you would find there'd be a cusp here. Okay, let's move on. I'm going to go out of this screen, which brings me back to the home screen. I now have a linkage in the bucket, so to speak. Things have been calculated, so I'm able to plot and print stuff. So let me show you the plot screens. This plot select screen lets you pick from 4 flavors of plots. Here we have 4 plots on a single screen, 2 plots on a single screen, 4 plots, one on top of the other. Actually 1 to 4 plots. You can have any number here. And this is polar plots, which I'll describe by example. Let's look at this first. I double click on that icon and it takes me to this screen. This icon reminds you of what you've chosen. Over here you have a bunch of what I call presets. I've put together collections of things like all the thetas, the omegas, the alphas, the velocities of various points on the links, accelerations of various points on the links. I can pick any one of these, and when I do, notice that these boxes down the bottom become populated with those items. And if I now say next, I will see the 4 plots. Now I chose 4 accelerations, and notice that alpha 2 is 0. Well, we told it to be. We're doing the constant speed of crank, which has 0 angular velocity, but we do have non-zero angular velocities for the other 2 links, alpha 3 and alpha 4, and I'm showing as the 4th item the so-called velocity ratio omega 4 over omega 2. Well, if you don't like that, you back up and pick something else. Look at all the thetas, for example. See the theta marching up steadily because we have constant speed on the crank, going from 45 to 405, but the other thetas are changing as the links rotate. If you don't like my collections of things here, you can go to this mix and match menu. This blanks out or becomes dim, and down here now I can pick anything that has been calculated so far. Let's pick, I'll take the one off the top of the list. Acceleration of the coupler point. Now that's a vector that is not along the z-axis, so I have to tell it what direction I want to look at, what component I want to look at. So I'll pick the x component for that box. I've got to pick 4 things here. And I'll pick the y component for this box, tell it OK. When I tell it OK, they appear down here in the queue. So let's pick something else, maybe acceleration of I34, and I'll take the x of that. And acceleration I34, we'll take the y of that for the 4th item. I force you to take 4 things here because you've asked for 4 plots. So now I'm looking at whatever I picked, acceleration of coupler point x and y, I34, x and y. Now notice over here, this says coordinate system is global. So these are referenced to the big X, big Y coordinate system, which is through the essentially the ground link. In this case, I guess I've rotated the ground link up 30 degrees from that axis, so it's not fair to say that. But it's centered at the fixed pivot of link 2 and parallel to the horizontal for the x-axis. I don't have to do that. If I back up a step here, pick the same stuff, actually to make things go quicker, I'm going to pick one off the preset formulas up here so I don't have to do all that mousing around to show you this. I can have either global or local rotating. Now I picked again acceleration I34, so we'll see one of the ones that we saw before. Switch it to local rotating. And this is interesting. You may or may not recall, I'll show you again in a second, that the x component of acceleration I34 in the global system had positive and negative values. Here it has only negative values. You should think about why that might be true. Here is the acceleration of I34 in the y direction in the local rotating coordinate system. So this coordinate system is painted on a link 4 in essence and is rotating with it. It's located, its origin is located at I34. So I can take my choice of coordinate system if I have chosen an item that allows that. for which it makes sense. So I could do the same for the coupler point. Let me go back and do acceleration of Mrs. Center 3, 4, but leave it in the global. And here's what I was pointing out to you before. The x component in the global system has both positive and negative values. The x component in the local rotating does not. Okay. Let's go back into the plot screen and look at something else. Here's a two plot per window. I can do the same thing here. The presets, the mix and match. I'll just show you one for an example. Alpha 3 and Alpha 4. Really no difference here except that I'm using 2 per screen, thus I have more real estate to devote to each and I get bigger plots, fewer of them. On both the previous screen and this, you see the link lengths and the initial conditions being fed back to you in boxes that you cannot change at this point. You have to go back to a calculation screen for that. If I back up, and if I keep backing up, I'll end up back at this menu. Go down, pick this guy. Now I can also pick, say, alpha magnitudes of all links, and now I'm going to see them sitting on top of one another. Different way of showing the same data. I can switch the background from light to dark. Dark looks better on the screen. I don't want to use that on my printer. I'll use ink up too quickly, so I'm going to switch to light if I want to print this out. The same information is fed back to you. On this particular screen, you can add fills for whatever they're worth. You can add horizontal grids, vertical grids, etc. Back to the plot screen. Let's show you this one. This is so-called polar plot. Now the menu is a lot smaller here. The only things that this is relevant to are vector information that are not along the z-axis, which would exclude such things as the omegas and the alphas. We're in a two-dimensional world here. Remember that all of your angular information, angular velocity, angular acceleration, they're all vectors, but they're vectors that live normal to the plane that we're investigating. That is, they're along the z-axis. So thus we can just indicate them by a magnitude. Their direction is the same in all cases. That's not true of these other vectors, the accelerations of the various points on our links and likewise the velocities thereof. Those are in fact vectors in the xy plane. So let's choose one that we looked at before, which is that's a very interesting set of data because I've fiddled around with the shape of that linkage. So we have rather a wild looking acceleration path, but that's alright, that's what it really is. I'm going to turn off this envelope. I'll explain what that does in a second. I'm going to put this into pause mode so that you can see these appear one at a time, and maybe that will make a bit more sense. Theta 2 up here is going to increment by whatever increments we asked for. Here we're going by 10 degrees starting at 45. So the first one is 45 degrees. So the crank is at 45, but my acceleration is up to the right something like 20 degrees. As I step this through, you'll notice the acceleration vector. This is actually the vector of acceleration of this point, which is the coupler point that we're observing. And these angles to the right are increasing every time I hit the step button. So now the acceleration is virtually downward. And now it's coming back over to the fourth quadrant. And now it's going to go back up into the, whoops, it went all the way to the second quadrant from the fourth. Drastic change in direction. Now it's over in the fourth quadrant, in the third quadrant. Second quadrant heading for the third, I should say. Still in the third. I'm up to 225. I'll just keep hitting the button here. And around she goes. And now I'm at 385, 405. There's the whole picture. Now that's what we saw initially. Now if I turn on this envelope, all that does is connect the dots from vector tip to vector tip. So that gives me a sense of the pattern. I can now turn off the vector lines altogether, and this kind of gives me an overview of the pattern of accelerations that this coupler point is experiencing. Quite interesting pattern in this particular case. Now, this again is the global coordinate system. So what I want to do is, without changing anything else, I'm going to back up, and I'm simply going to select that same item again, acceleration of the coupler point, switch to local rotating, no other change. And a totally different pattern emerges. Let's put the vectors back on. Still looks equally weird, but things are pointing in different directions. Now, it's the same acceleration, but my coordinate system is now different. My coordinate system is now rotating with the link, in this case the coupler, not fixed to the ground plane. That's the difference. So far I've shown you how to input data, how to animate it, how to plot it, how to print it. One thing I didn't show you about in the print, which I want to return to, actually I haven't shown you printing yet, have I? So far I've shown you input, animate, and plot. Now let's look at the print. Very similar menu comes up for selecting what you wish to print. Looks almost the same as the plot screens. So I can again pick off of the presets, or I can come down here to the mix and match as I wish. If I say next, I get a scrollable window. I can move this up and down and look at my various values. Over here on the right I have crank angle. Is alpha 2, alpha 3, alpha 4, omega 4 over omega 2. If I wish to print to a printer, go back to the same screen, select printer, pick something, it populates it down here. When I say next, it's going to bring up a screen to allow me to choose a printer that's available on my system. I'm not going to do that. You won't see me print anyway. And the third option here is to go into the print button and choose disk file. And this you may find quite handy. If whatever I pick here now will go to a disk file, it will be a text file stored on your disk in whatever location you choose to store it, so I can create a new folder or put it someplace on some disk. And when I do that, I can open it up in Excel or any other program that will open a tab delimited file. If I bring it into Excel, I can then plot the data differently than this program allows you to plot it. You can do some numerical calculations with the data, perhaps combine it with some other information that you have generated in your Excel program. So I think you'll find that fairly handy. I'm not going to show you the dynamics and the balance today. I'm going to save that for another video, and I'll end by showing you a few of the menu picks here. Clearly you want to save your data once you've got a solution that you like, so if I pull down the save or the save as, these work as in any other Windows-based program. I get a browser. I can type in any label I like for my file. It should automatically add the .fourbar suffix, which is what the program is looking for when it opens a file. You can browse to place this wherever you like, on a floppy or whatever. And of course it doesn't have a floppy in it right now, so it's going to bark at me. So that's pretty standard. Once you've saved it to disk, you can later on open it with the open command. It's warning me that I have not yet saved my data, and before I open a file, I should save it if I wish to keep it. Otherwise, I'll overwrite it. I'm not going to save this. I was just playing around, so I don't care about it. This again gives me a browser. I can choose to find, look for a file someplace that I've stored earlier and open it up. If I choose New, then what that's going to do is essentially zero all the buckets in the program, throw away what I've already calculated. And again, it warns me by suggesting I might want to save it first. I won't bother. And I ask you to confirm it because there's no recovery from this. Right now, it's all gone. I can access a few examples that I've built in, which you might want to look at to see various types of coupler curves and what linkages behave like. These are linkages that are described in the book. I can change the unit system. I've got it defaulted to work in the American system of inch-pound seconds. You can switch to foot-pound seconds. I'm not quite sure why you'd want to do that. Here's true SI, meters, kilograms, seconds. I also have two modified SI systems in which we keep the masses in kilograms and the time in seconds and the forces in newtons, but I'll let you put your lengths in either centimeters or millimeters. Meters are a little bit large for most of the machine design linkage work that you encounter, so these may be more convenient. I'll leave the cognates and the synthesis and the other stuff for another day. I guess I've already mentioned the help menus, so there's no need to revisit that. You can find out what version of the program you're running from this. This splash screen comes up when you run the program as well. And you can tell something about the student version here. So I'm going to stop here. I've gone on long enough for the first video, and I will pick this up again with some additional information on how to use some of the more advanced features. Try the program, have fun, you can't break it, see what you can do with it, check your homework. I don't think your instructor is going to want you to do the homework out from this program, but you certainly can check your answers. We'll see you later.